So in this video, we're going to do sort of a review of some periodic trends from general chemistry and also intermolecular forces of attraction. So these are going to be forces of attraction that hold molecules near each other. These are not the same as actual covalent bonds. The periodic trends that we're going to talk about are those that are going to concern us in this class. And I want to spend a little extra time on two different types of intermolecular forces of attraction that we kind of, we don't really spend a ton of time on them in Gen Chem. We talk about them, but we sort of pay a little bit more attention to things like hydrogen bonding or dipole-dipole interactions. And those things are going to be important in organic chemistry. But the dispersion forces, the weakest intermolecular forces of attraction, which can become more significant depending on the mass or the sort of arrangement of the groups on a molecule, that actually really matters to us in organic chemistry, a little bit more than we sort of give it credit for in Gen Chem. So I'd like to pay a little more attention to that. And then we're going to come back in the next video when we talk about acid-base review to bring up these dispersion forces again. And then the other intermolecular force of attraction that we talk about in Gen Chem, and it is the strongest, is the ion dipole interactions. We just mention those, right? But we don't really talk a ton about them. And so in organic chemistry, we actually will choose very particular solvents for certain reactions based on whether or not we can have an ion dipole interaction and use that to our advantage. So it might behoove us to actually just spend a little more time on those two in our review. So I want to start just with a reminder of some basic periodic trends. So in general chemistry, we talked about how if you're staring at the periodic table, there are some general trends. Again, these are just trends. There's, exceptions to every rule. And a lot of these trends actually are a lot more exceptions than rules. But the two that we typically sort of like focus on in terms of making sense out of stuff in organic chemistry would be electronegativity. So again, that's going to, lend itself to understanding polarity, which we already discussed in the bonding video, and also atomic radius, which will be important to us, believe it or not, in acid-base chemistry when we want to sort of take a qualitative stab at deciding the strength of an acid. So in terms of atomic radius, we're looking at a decrease as we go from, let me move this periodic table over. If we go, do this in a different color for you. From left to right, across the table, we notice an increase, a decrease in atomic radius. Right, so like if you're going across a period, what you notice is that you're adding protons to the nucleus, right? And you're adding electrons, which is true, to at the energy level, but you're not really increasing the distance between those electrons that are being added and the growing nuclear charge. So what ends up happening is you increase the effective nuclear charge or the core charge, and the size of the atom tends to shrink because those electrons are more and more attracted to the center of positive charge. So we start to notice that as you go across a period, you decrease the radius of the atom. As you go down a group, we're adding shells. So yes, you're adding more protons, but you're also increasing, in this case, the distance between the added electrons and that growing nucleus. And so we tend to notice an increase in atomic radius as we go down a group. I'll just abbreviate this AR. So lithium is going to be much smaller than cesium, right? Another trend that's important to us, I'll color your lake here, we'll just pick this one, I guess, is as we go down a group, I'll do it on this side, we noticed that if we wanted to focus on, say, the strength or the fierceness with which an atom is going to hang on to its valence electrons, or the attraction it's going to have for somebody else's valence electrons, right? In other words, it's electronegativity, and I'll abbreviate that En. We're going to notice that we have a decrease in the electronegativity as we go down a group, or in other words, there'll be an increase as you go up a group. As we go across periodic table to the right, we have an increase in electronegativity. So from another video we were discussing, if you went diagonally across from the bottom left to the top right of the periodic table, you'd have a general sort of upward trend in an increase in electronegativity, where fluorine of all the bonding atoms is going to hang on to its valence electrons the most fiercely. It's also going to be most attracted, right, to somebody else's valence electrons if sharing electrons in a covalent bond. Cesium, right, is going to be, of the bonding elements, it's going to have it'll be the least electronegative. So in other words, it'll be more or most likely to sort of donate its valence electrons. So these are sort of like the two major trends that are going to help us sort of wrap our minds around some of these properties, these physical properties coming up. I want to talk first, specifically in this video, about intermolecular forces of attraction and how these affect certain physical properties. We care more in organic chemistry. So it's like, in Gen Chem, you're talking about viscosity and capillary action and surface tension and all that. And that's fine. That's great. In Orgo, we're interested in like, hey, why is this more acidic than this? Why is this more basic than that, kind of a thing, right? So that's where these intermolecular forces of attraction are really going to interest us. It's the behavior of a molecule. So I'm going to talk just a little bit here about the different types of intermolecular forces of attraction. I'm just going to abbreviate this IMF. So these intermolecular forces of attraction are going to be forces of attraction or attractive forces that hold molecules near each other. So for example, if you have a glass of water and you're hoping to convert that liquid water into a gas, in other words, you want to, in your mind, you're probably thinking, I want to boil the water, right? But really, from our point of view in chemistry, we're just going to change its physical state. We're going to take it from a liquid phase to a gas phase. So there's different ways that we can do that. The most immediate way that people might dream up would be to heat it, right? But all you're doing there is increasing the average kinetic energy of the water molecules so that you're basically busting up the intermolecular forces of attraction, holding the water molecules near each other in the liquid phase in the first place. You liberate those water molecules from the liquid phase and allow them to enter into the gas phase, where the intermolecular forces of attraction are all the same, but they're a little less significant because the molecules are farther apart. They're spaced farther apart, right? But you don't change the intermolecular forces of attraction. The attractive forces that exist between water molecules are going to be the same no matter what phase they're in. It's just how significant are they? Some of these forces of attraction are going to be stronger than others. We'll start with the weakest one, and that's going to be what we call dispersion forces. Dispersion forces in Gen Chem, we talk about, these are our weakest, and everybody has them, even just individual atoms. Dispersion forces are basically, if you imagine, a fleeting dipole moment. or you could say instantaneous, dipole. So for example, you could have all of the electrons in an argon atom all of a sudden just move over to one side of the atom, right? And so on that side of the atom, you've got a partial negative charge has built up. On the other side, where they've left, you have a fleeting partial positive charge. That's a dispersion force. So in Gen Chem, when we talk about these being the weakest, it doesn't mean that they're inconsequential. It just means that they're not like, super high in energy. But they can become more significant the more electrons you have. So we also in Gen Chem talk about the mass of the substance. The greater the mass, the more electrons you have to polarize. So we can create a larger partial negative charge and a larger partial positive charge, or in other words, a more significant dispersion force if we have a larger species. You can also do that if you have two species with the same mass, but you've changed the configuration of how the groups are arranged. So if I cluster things up, it's more difficult to polarize the electrons, right? So we notice that with like different isomers of molecules. These like molecules have the same molecular formula, but different arrangement of the groups or different arrangement of the atoms on the species with different boiling points. So one of the physical properties that are affected by these intermolecular forces of attraction would be the boiling point. So in a dispersion force, what we could say, just take like an average sort of atom. We could talk about this happening with a molecule as well. We have these shared electrons. We'll just use little dots here. In any one moment, you could say, well, what if both of these electrons went over here? So now what ends up happening is I create a partial positive charge on one end and a partial negative charge on the other. The partial negative charge is going to be where the electrons went to, right? Because they're negatively charged. And the partial positive charge is going to be sort of like the other end, where it's like, hey man, I'm deficient in electrons now. It's not a formal charge of like +1, +2, or whatever. It's a partial positive and a partial negative charge. In other words, it's a fraction of a positive charge or a fraction of a negative charge. And these are going to be our weakest intermolecular force of attraction, but it can become more significant depending on the species. So I'll say depending on the mass. So depending on the mass, in other words, the number of polarizable electrons in order to make that partial positive or partial negative charge, or structure. Physical properties that we talk about being affected by this in Gen Chem are usually just boiling points or like vapor pressure or something like that. But in organic chemistry, when we get into substitution elimination reactions and we're using molecules that have atoms with lone pairs of electrons, things that have, say, a nitrogen that has, say 3 covalent bonds and a lone pair, or in other words, 2 non-bonded electrons, those non-bonded electrons can be used to attack something else and create a new bond. They can also be used to abstract a relatively unhindered proton. So we could use those electrons as a base, right? And then when we start talking about how basic a molecule is, these dispersion forces become a little bit more important to us. Because if we can increase the partial negative charge on, say, that nitrogen, or in other words, we can localize those electrons on that nitrogen, make them more available for attacking, right? Either a proton or some, electrophilic portion of another molecule, then all of a sudden these dispersion forces help us sort of rationalize why one molecule might be more basic than another. And as we get into the acid-base chemistry stuff, I'll talk a little bit more about these dispersion forces and remind you of, hey, look at this molecule. The dispersion forces are more significant. That's going to make this a little bit more basic. So it's one of those physical properties that's going to be affected by these forces of attraction. And the next one that we talked about in Gen Chem were the dipole-dipole interactions. This is another one of those partial positive, partial negative charge interactions. So we can call this a dipole-dipole interaction. Where we have a partially positive end or portion of one species is attracted to the partially negative end of another. So for example, I could have like an acetone molecule. So let me draw this a little bit suggestively here to make it easy to see. So here's acetone. And I can draw the dipole end. Oops. So there's your dipole moment, right? So in other words, we have a partial positive charge on this carbon. Oxygen is more electronegative than carbon. That's one of our periodic trends, right? There's going to be a partial negative charge up above that oxygen. And so this, if you put this into a sample with other acetone molecules, we just have a glass of acetone, right? We have an attraction between these two dipoles. So again, it's the same molecule. We have a partial positive charge here, partial negative charge here. And this right here is our dipole-dipole interaction. So there's a force of attraction there where that partial negative charge on the oxygen on one acetone molecule is attracted to the partial positive charge of the carbon on the other acetone molecule. So this is what we call a dipole-dipole interaction. And then there's another intermolecular force that is a dipole-dipole interaction, but it's very specific. This particular intermolecular force of attraction is like our medium strength. So it's stronger than a dispersion force if you're talking about molecules of comparable mass, right? If you've got this big giant molecule that only has dispersion forces, but it has like a mass of say 400 grams per mole, and then you've got little teeny acetone over here, yeah, the dispersion force on the bigger molecule is going to be more significant. But if you're talking about comparable masses, the dipole-dipole interaction is a little stronger than the dispersion forces. A dipole-dipole interaction that's very special to us and is a little bit stronger is called a hydrogen bond. So hydrogen bonding is not a covalent bond. And in some courses, they make it seem like hydrogen bonding is it rivals a covalent bond. It actually kind of doesn't. It's probably along the lines of like 40, 50 kilojoules per mole in terms of its energy, whereas a covalent bond might be more like 200, right? So it's definitely more significant in its strength than a regular dipole-dipole interaction, depending on the mass of the species. And again, depending on the mass of the species, it's definitely going to have some more oomph than, say, just the dispersion force. But this is basically going to be a dipole-dipole interaction between two molecules where you have sort of an electronegative, a more electronegative atom that has a hydrogen directly bonded to it. So there's going to be a partial negative charge on a more electronegative element like oxygen or nitrogen is usually what we focus on in organic. And that oxygen or that nitrogen is going to be directly bonded to a hydrogen. And that hydrogen will have a partial positive charge. And so that dipole-dipole interaction between two molecules that have that setup, that special dipole-dipole interaction is called a hydrogen bond. So we have a dipole-dipole interaction between, well, I should say between molecules where either an oxygen or a nitrogen is directly bonded to a hydrogen. So let's draw what that might look like. We could take something as simple as methanol. So CH3, and I'll expand this bond so that we can see what's going on here. We have an oxygen or a nitrogen. So here we have an oxygen. The oxygen has two lone pairs of electrons, or in other words, 4 non-bonded electrons. It has a dipole going in this direction, right? So we have a partial positive charge on the hydrogen. There's a partial negative charge on the oxygen. And if I were to draw another methanol molecule, I would have here, and draw it backwards to make it easier to follow. Another situation where we have a dipole, and again, partial positive charge on the hydrogen, partial negative charge on the oxygen, and there's going to be a dipole-dipole interaction between these molecules. And because we have a hydrogen involved, this dipole-dipole interaction is special and we call it a hydrogen bond. So of these three, this is going to be the strongest, but it is not the strongest intermolecular force of attraction. In some courses, they do say hydrogen bonding is the strongest intermolecular force of attraction. No, it's not. We have another one that's actually rivals a covalent bond, and we use it frequently to sort of rationalize why we choose certain solvent systems over others, or as part of our rationale anyways, in organic chemistry. So this is going to be a stronger. When I say strong, medium, weak, I'm talking about the energy. So this will be a stronger intermolecular force of attraction. And what do I mean by strong, medium, and weak? So if we're talking about molecules that are of comparable mass, you might say that if that molecule, if they all have the same sort of molecular weight within, say, 5 grams per mole of each other, if one of those molecules only has dispersion forces, you can bank on like a half a kilojoule per mole for the dispersion force, maybe 20 kilojoules per mole for the dipole-dipole interaction, if that, maybe 15 or 20, and then like 40 or 50 for the hydrogen bonding. right? Whereas a covalent bond is more like 200, 250, 966 or something like that. They're a lot higher in energy. The strongest intermolecular force of attraction is our ion dipole interaction. This is where you're going to take a polar molecule, so you're going to have a partial positive end and a partial negative end of your polar molecule, right? Just like you would with your dipole-dipole interaction, or say your hydrogen bonding or whatever. It's the same idea. Something like methanol, something like water, whatever. And a salt or some ionic compound, where if that salt is going to be soluble in that polar molecule, like water, for example, is going to dissolve, say, sodium chloride, then when the ionic compound dissociates, you end up with ions where one of them has a negative charge and one of them has a positive charge. So you can kind of imagine what's coming next, right? It looks like a dipole-dipole interaction, but one of the compounds is ionic and it has dissociated. So it actually has formal charges. The cation is going to be attracted to the partial negative end of your polar molecule, and the anion is going to be attracted to the partial positive end of your molecule. So we could keep it simple by just drawing something like water. Maybe like just this. Keep it easier to see. And I have a partial negative charge up near the oxygen. And I'm going to put these here by symmetry. In Gen Chem, you probably remember discussing that the center of positive charge is between the two hydrogens, right, in that bond angle there. But I'm just going to put that, I'm going to draw the molecule like this. Then I'm going to say, imagine that I'm going to center my partial positive charge between the two hydrogens. These are just illustrations. This is not anything that you're going to have to sort of regurgitate or anything. I'm just giving sort of like a general description. When we're talking about these dipole moments, we have this one that is just sort of shooting up the center of the water molecule. It's sort of two added together. And remember, with the bonding and the molecular geometries with these, you can have polar bonds and have a non-polar molecule. Carbon dioxide has polar bonds, but it is non-polar overall because the vectors are going equally in opposite directions. In the water molecule, it's bent, right, like a boomerang. So the two vectors are actually pointing up toward the oxygen and they're going to be added together. So we have one big dipole going up the center of the molecule. If I were to draw in some salt, say we'll put potassium chloride. When this dissociates, we have positively charged potassium and negatively charged chloride hanging out near these partial positive and partial negative ends of the polar molecule. This is our strongest intermolecular force of attraction. This can be over 100 kilojoules per mole. And here's the point where usually in Gen Chem, we just give this example and we're like, and this is the strongest, and have a nice day. Like, here's an ion dipole interaction. In organic chemistry, I want to show you that in this moment, I have drawn for you a polar molecule that is considered to be protic. And by that, I mean it has hydrogens that can hydrogen bond, right? So this is a polar protic molecule. So I'll put that in parentheses up here. We'll come to a chapter where we're discussing substitution and elimination reactions, and we're going to be picking the solvent very strategically for some of our reactions. And in some cases, we'll say this works better if you use a polar protic solvent, and we'll remind ourselves of the ion dipole interaction and why this is a good solvent to pick, why these properties of this particular solvent are considered to be good to have for that particular reaction. There is another type of polar molecule that is considered to be aprotic. So I can have another ion dipole interaction example to show you, but this one is going to be polar aprotic. So in other words, it is not going to be able to hydrogen bond. You want two things to react. You want them to be available to react. You don't want one of them to be hanging out with the solvent, hanging out in the corner, chatting with the solvent, hydrogen bonding away. You know what I mean? So, but you need it to be polar, right? So that your stuff dissolves. So this is where you have to get sort of strategic about the solvent that you choose. You might also have a situation where you're using a reagent that is a salt. So you need to be able to dissolve it, and you'd really appreciate it if the cation, for example, were babysat by a section of the solvent while the business end, the anion portion of the salt, got busy and reacted, right? So this is where you can pick a solvent that is polar but cannot hydrogen bond with your stuff, right? So it doesn't get in the way of the reaction, and it can keep, say, one of the ions busy from your other reagent. A great example of this solvent like this is dimethyl sulfoxide. And that looks like this. Remember, with hydrogen bonding, the hydrogen has to be directly bonded to the more electronegative atom. Let me put in the charges on here. I'm not going to draw the dipole arrows because it'll just clog things up. But notice how on the outside of this molecule, we have oxygens with partial negative charges. And in the center of the molecule, we have a sulfur with a partial positive charge. So it's not a formal charge. It's just the electron density is being pulled in the direction of the oxygen. And so there's a partial positive charge on the sulfur. It's hidden, it's sort of nestled in the interior of the atom. So you don't have to worry so much about the anion portion of your other reagent if you were to dissolve something like a salt in this stuff, sort of getting tangled up with that partially positive charged sulfur. What you might notice, though, is that you can coordinate the cation portion. So I could take something like that and create an ion dipole interaction with my polar aprotic molecule, dimethyl, so DM sulfoxide, SO. So if I was going to be using something, for example, like sodium methoxide, and really what I'm interested in isn't so much the sodium because it's spectating, but I'm interested in this portion of the molecule, and I want that portion of the molecule to be free to attack something else. I need to be able to dissolve it. I don't want to use water because I can hydrogen bond, right? I can hydrogen bond with the methoxide portion. And I don't want that to happen. I want that oxygen to go buzzing off and attack something else with those lone pairs of electrons. I can babysit the sodium with DMSO. I'm not going to tie up the methoxide portion of the molecule with the partially positive sulfur because it's sort of nestled in the interior of the atom. It's a little clustered, right, in there. And so what I've done is I've created a situation where now I have a sweet little base, or a sweet little, what we're going to call later, a nucleophile, something that's going to use its electrons to attack something else and form a new bond. So if I'm looking for a specific situation where I want to take ion dipole interactions into consideration and use them to my advantage in a synthesis, I want to think about what I'm actually doing. What type of a reaction am I doing, and what are the other reagents that are in the pot? Let's see. So these are the intermolecular forces of attraction that I wanted to talk about. Some of the physical properties that are affected by these, and we'll just briefly list them. We talk more in detail about these in Gen Chem, but just as a reminder, some physical properties. That are going to be affected by intermolecular forces of attraction. You have to sort of ask yourself, like, what are these physical properties? As in, how do we sort of define them? Like, how do we describe them? What is actually going on? And then you get a better understanding of, like, okay, if I have some significant intermolecular forces of attraction going on here, then I'm going to have to put more energy into the system, right, to peel these molecules away from each other. So for one thing, we notice that vapor pressure is affected. You have a glass of water and it's sitting on your desk at room temperature, it's mostly going to be hanging out in the liquid phase, right? So at, say 1 atmosphere of pressure at sea, pretend you're in Boston, right? Just 1 atmosphere of pressure. Um, that's the external pressure, right? On your column of water, your liquid water. Right above the liquid phase, you have some water molecules that have sufficient kinetic energy such that they were able to break free from their intermolecular forces of attraction and enter into the gas phase. So the intermolecular forces of attraction are all going to be the same, as in you can still hydrogen bond, still have dipole-dipole interactions, and everybody has dispersion forces. We haven't eliminated the intermolecular forces of attraction, but we've separated the water molecules into the gas phase. So now those forces of attraction are less significant, right? But that pressure of the gas, the water molecules in the gas phase just above the liquid layer, that's what the vapor pressure is. And the vapor pressure and the boiling point kind of go hand in hand. You have to ask yourself what the boiling point is. A lot of people immediately think temperature. That's just an easy way to get your stuff to boil, but what does it mean to boil in the first place? So you have to think about what the vapor pressure might be. If I have really strong intermolecular forces of attraction like water does, you imagine the vapor pressure is going to be pretty low, right? You'll have more water molecules in the liquid phase at room temperature than you will have water molecules in the gas phase. Some of them do, like you'll have a fraction of those water molecules with sufficient energy such that they can overcome the intermolecular forces of attraction and enter into the gas phase. And that's totally fine, right? I mean, evaporation occurs, right? You don't expect that glass of water to have the same volume of water molecules if it's left uncovered on your desk for a month, right? You expect some of that to evaporate. And that can only happen if some of those water molecules are free to break out of the liquid phase and enter into the gas phase below the point at which you would expect the sample to boil. But then again, what does it mean to boil? Well, the boiling point is the temperature at which the vapor pressure of your liquid equals the external pressure. So in other words, if you were to drastically decrease all of a sudden the atmospheric pressure, right, the outside or the external pressure, then all of a sudden the temperature at which your stuff boils, or the temperature at which those two pressures, the vapor pressure and the external pressure, are going to be equal, is going to be a lot lower. right? So the stronger the intermolecular forces of attraction between these molecules, and we're talking like a pure sample. I'm not talking about a solution, like something dissolved in water, or like a glass of wine or a glass of juice or something like that. Just a pure sample of acetone, a pure sample of like butane or whatever, right? So the more significant or the stronger those intermolecular forces of attraction are, then the more attracted the molecules are going to be to each other, and the closer they're going to be, your vapor pressure is going to be a lot lower. If those intermolecular forces of attraction are super weak and the molecules are like, whatever, dude, like, I'm not super psyched to be next to you, then you expect a higher vapor pressure, right? The pressure of the gas above that liquid at a given temperature is going to be greater. The other thing that's affected by increasing or decreasing intermolecular forces of attraction would be like surface tension. So the surface tension is sort of almost kind of like a skin in a weird kind of way. So you've seen bugs that can stand on top of like water droplets, or you've ever seen like nature documentaries where they show an ant or some bug is sort of like piercing a water droplet to take a drink, and you actually can see it magnified where they stick their little straw in there, and you can watch the water droplet actually bend a little bit before it gets punctured, which seems insane to us, but to something that little like that, it's having to break that surface tension. What is that anyways? Why does it act like that? Well, if you have really strong intermolecular forces of attraction, then I'm going to just keep using water because it's easy to imagine, then those water molecules or whatever molecule you have, right? The stronger those forces of attraction are, then the molecules that are on the surface are going to be attracted to their own kind, right, of molecules deeper in the sample. And so it's going to pull in on itself, and it creates almost like a little skin on the outside. That's the surface tension. So the greater the intermolecular forces of attraction, the greater the surface tension. Viscosity is another one. So this is basically a measure of a liquid's resistance to flow. Now, if you take temperature out of it, because obviously we know that the viscosity of something is going to increase if you decrease the temperature. Think of maple syrup, for example. If you heat it up, it flows. If you cool it down, it gets like stuck to itself, right? But if you take that and just hold the temperature constant, imagine just the intermolecular forces of attraction between different types of molecules. If you have a molecule with greater intermolecular forces of attraction, then you're going to experience a higher viscosity. So those molecules are going to be more attracted to hanging out with each other. And if they're in the liquid phase, they're not going to flow as freely. Capillary action is another one. So this is sort of like a two-parter, right? Capillary action. You're talking like taking a molecule in the liquid phase and, say, pushing it up, I guess, the stem of a flower or the trunk of a tree or something like that. And so you have these intermolecular forces of attraction between the molecules that are in the liquid phase. You also have molecules that make up the inside of the stem. And so there's going to be attractive forces between the molecules in the liquid phase and the inside of the stem. And then there's going to be attractive forces between just the molecules in the liquid phase. And there's this push-pull kind of thing that happens. And that capillary action can, as you're driving the liquid up the stem. And that's affected by the strength of the intermolecular forces of attraction. If you have a situation where you have a molecule that's super attracted to itself and not super attracted to the molecules that make up the inside of the tree trunk or the stem of the flower or whatever, the capillary action is going to be affected by that. So the molecules that are in the liquid phase are going to be more attracted to hanging out with each other. Let's see, I think of another one. Oh, if you have a solution, if you want to make a solution, you can also think solubility. So that term like dissolves like, they're talking about intermolecular forces of attraction. That's what the quote unquote like means. So, for example, if I want to dissolve something like, you know, propane or butane in a glass of water, it's probably unlikely to happen, right? Or oil, right? Because most of the oil is nonpolar. Butane and propane are nonpolar molecules. They only have dispersion forces. And so they don't share similar intermolecular forces of attraction with water molecules. So the solubility is going to decrease if you have decreased amounts of shared intermolecular forces of attraction. Whereas if I took something like methanol or ethanol, some small alcohol that can hydrogen bond, that has dipole-dipole interactions, also dispersion forces, because everybody does, they share similar intermolecular forces of attraction with the water molecule. And so they're going to commingle a little bit easier. They're going to coexist, you know, and so the solubility is going to increase when they have an increased sharing of intermolecular forces of attraction. Okay, so that's going to be it here for this with general periodic trends, intermolecular forces of attraction, and the physical properties affected by them. In the next video, we're going to review acid-base chemistry, and we'll pull in some of these intermolecular forces of attraction and some of the descriptions for those.